Next topic, the topic which we are going to see is the Maxwell's equation. This Maxwell's equation is framed by James Clerk Maxwell in the year 1865. He framed the theory of electromagnetic radiation by using four equations, and he explained the basic relationship between electric and magnetic field. These four equations are called as Maxwell's equation. He formulated this fundamental, that is Maxwell's equation, based on four fundamental laws. First, Maxwell's equation is based on Gauss law of electricity. Second one is based on Gauss law of magnetism. Third one is based on Faraday's law of electromagnetic induction. And fourth one is based on Ampere's law. So the four Maxwell's equations are del dot D is equal to rho, del dot B is equal to 0, del cross E vector is equal to minus dou B vector by dou T, and del cross H vector is equal to J vector plus dou D vector by dou T. These are all the four Maxwell's equation. So the first equation is from the Gauss law of electric field. Second one is from the Gauss law of magnetic field. Third one is from the Faraday's law, and fourth one is from the Ampere's law. Now we are going to see how to derive these equations. That is, we are going to discuss the derivation of obtaining the above equation. So equation 1, that is Maxwell's first equation from Gauss law of electric field or electric Gauss law. So here we are considering a dielectric medium. That dielectric medium of surface, the surface is S, and that dielectric medium is bounded by a volume, and the volume V. It is bounded by a volume V, and it contains the charge. So the charge is denoted by the total charge in that dielectric medium is considered as Q. Then, according to Gauss law of electric field, we are considering that the closed surface integral of E vector, that is electric field with intensity, into ds is equal to the charge enclosed, the total charge enclosed in it, divided by epsilon naught. Here we can bring this epsilon naught to the right hand side, left hand side. When you bring this epsilon to here, it becomes closed surface integral of epsilon naught into E vector dot ds is equal to 0. And we know from the basic thing, d vector, displacement vector, electric displacement vector, d vector is equal to epsilon into E vector. What is epsilon? It is a permittivity. Permittivity is equal to relative permittivity into free space. Relativity of a free space. This is relativity of a free space, and this one is relativity of a medium, or relative permeability, or dielectric constant, anything we can say. So this d vector is equal to what? Instead of epsilon, we can write it as epsilon naught into epsilon r. If a medium that passes is a perfect dielectric, or that perfect dielectric medium is an air medium, means we can say that for an air medium, epsilon r value is equal to 1. That is, relative permeability value is equal to 1. So d vector is equal to epsilon naught into E vector. So when you substitute this in the above equation, that is, in this equation, instead of epsilon naught E vector, if we substitute d, what happens? A d vector is equal to, that is, closed surface integral of d vector dot ds is equal to Q. This is our third equation. Now we can see what is the total charge. The total charge is equal to charge density over a volume. That is, closed volume integral of rho into dV. So this is a Q. You substitute this in the equation 3 instead of Q. When you substitute, it becomes closed surface integral of d vector dot ds is equal to closed volume integral of rho into dV. This is the Maxwell's first equation in terms of integral form. But we need to convert it into a differential form. So to convert this equation, Maxwell's first equation into a differential form, we have to convert the surface integral to volume integral. To convert a surface integral to volume integral, what theorem we have to use? We have to apply a Gauss divergence theorem. So using Gauss divergence theorem, we can convert the surface integral on a left-hand side to a volume integral. That is surface integral of closed surface integral of d vector dot ds is equal to closed volume integral of del vector dot d vector into dv. So instead of this thing, we have substituted this one. So both the sides we have a what? Volume integral. Two volume integrals are equal if these integrands are equal. Both the integrands are equal. Now both volume integral are equal. So here it becomes del vector dot d vector is equal to rho. This is the Maxwell's first equation in a differential form. Now we can go for a Maxwell's second equation. What is our Maxwell's second equation? We are deriving Maxwell's second equation from a Gauss law of magnetic field. What is a Gauss law of magnetic field? It is a magnetic flux through any closed surface is equal to 0. Magnetic flux passing through any closed surface is equal to 0. That is magnetic flux, it is pi. When it is passed through any closed surface, that value is equal to 0. Magnetic flux pi means, what is pi vector? Pi magnetic flux in terms of magnetic induction, it can be written as magnetic flux is equal to closed surface integral of magnetic flux density. That is B vector, magnetic induction or magnetic flux density. B vector dot ds. So comparing the above two equation, that is when you compare this, then you substitute this 10th equation in 9. Instead of pi, it will be what? Closed surface integral of B vector dot ds is equal to 0. This is the Maxwell's second equation in terms of integral form. Then to convert it into differential form, we need to apply a what? Gauss divergence theorem. When we apply a Gauss divergence theorem, here the surface, closed surface integral of B vector dot ds is equal to closed volume integral of D vector dot B vector into dV is equal to 0. So the surface bound over a volume is an arbitrary. Therefore, the equation holds a the integral vanishes. So it becomes del dot B vector is equal to 0. This is the Maxwell second equation in differential form. Now we can come for a Maxwell third equation. Where it is derived from? It is derived from the Faraday's law. So what is Faraday's law? It is then electromotive force is equal to rate of change of magnetic flux. Electromotive force is equal to that is a rate of change of magnetic flux. That is the Faraday's law. So what according to the thing, we know that electromotive force is in terms of electric field, we can write it as E is equal to closed line integral of E vector dot dl. Similarly, what is magnetic flux in terms of magnetic induction? It is pi is equal to closed surface integral of B vector dot ds. Substitute the equation 15 and 16 in the equation 14. When you substitute what it is, E is equal to line integral of closed line integral of E vector dot dl is equal to, what is right hand side we have minus d by dt of pi. What is the pi value? Surface integral of B vector dot ds. So these are all the, we also changes, that is we can bring the integral to the outside and differentiation inside. So it becomes minus surface integral of dB vector by dt into ds. This is the Maxwell's third equation in integral form. So how to convert this into a differential form? Here we need to convert a line integral to surface or surface to line. Then only both the side it will be same. Here we need to convert line integral to a surface integral. To convert a line integral to surface integral, what theorem we have to apply? We have to apply a Stokes theorem. So in the Stokes theorem, line integral of E vector dot dl is equal to surface integral of del vector cross E vector into dl. Comparing the above two equation, we get surface integral, closed surface integral of del vector cross E vector into dl is equal to closed surface integral of minus closed surface integral of dou B vector by dou T into dc. Both this, when the surface is an arbitrary, the integral will get vanished. Both the side is we have also having a same integral, so it is arbitrary, so it is getting vanished. If the integral vanishes, what happens? Del vector cross E vector is equal to minus dou B vector by dou T. That was our equation. That is the Maxwell's third equation in a differential form. Now, we are coming for a Maxwell's fourth equation. Where it is derived from? It is derived from the Ampere's law. Okay. So, what is Ampere's circuit law? Closed line integral of magnetic field intensity H vector is equal to into dl is equal to I. What is I? Current. Current is equal to surface integral of current density into ds. So, substitute this equation 22 in 21, we get closed line integral of H vector dot dl vector is equal to closed surface integral of J vector dot ds. So from the Stokes theorem, the line integral will shall be converted into surface integral. When we convert, what happens? Line integral of H vector, closed line integral of H vector dot dl vector is equal to closed surface integral of del vector cross H vector into ds. So comparing the above two equation, it becomes the surface integral of del vector cross H vector into ds is equal to surface integral of J vector dot ds. Both the side surface we have, it vanishes. It becomes del vector cross H vector is equal to J vector. Then, when we apply a Gauss divergence theorem on both the side of the equation, Gauss divergence is what? Taking a divergence on both the side. Divergence mean what? Del dot of A. That is del dot of, instead of A, we have what? Del cross H is equal to del dot J on right hand side. So vector identity, it is the common formula which we have to be remembered. It is del cross vector dot of del cross H vector is 0. It is a constant formula. When we substitute this vector identity in the above thing, the above equation 27 will become del vector dot J vector is equal to 0. But according to equation of continuity, what it is? Equation of continuity, we have know that del vector dot J vector is equal to dou rho by dou T. When you substitute this del dot J as 0, what happens? It will become the dou rho by dou T is equal to 0. So if a dou rho by dou T is equal to 0 means that the differentiation of a charge density, charge is equal to 0. Now, we can say that this charge is a constant. Charge density becomes a constant, or in other words, we can say that charge density is static. So what we need to, it is an in Ampere's equation is a valid for a state condition. Only it will have a varying field. When even it is invalid for time varying field. That is valid for steady state condition, not for a varying field. So here, what they are doing is, we are saying that this equation 26 is incomplete. To prove that it is an incomplete only, we have done all this part. So to complete that, what we are doing is, we are adding that del cross H vector, del vector cross H vector plus J vector. Instead of that, we are adding a term called as displacement current density JD. And again, we are taking a divergence. Left hand side will become 0 due to vector identity. And then right hand side is what? Del dot vector dot J vector plus del vector dot JD vector is equal to 0. So we all know that del vector dot J vector is equal to minus dou by dou T. Substitute this in the above equation. When you substitute, minus dou rho by dou T is equal to del vector dot JD vector is equal to 0. So del vector dot JD vector is equal to dou rho by dou T. So here, from what is the Maxwell's first equation? The del vector dot d vector is equal to rho. So instead of rho in the above equation, substitute del dot d. Bring this del outside and dou by dou t inside. So both the side we have both the del, it cancels. So jd is equal to dou d by dou t. So substitute this in the above equation. This equation, instead of jd, we are substituting what? Dou d by dou t. This is the Maxwell's fourth equation.